All right, because we just finished that exploration, this slideshow should be pretty easy. The main idea behind the slideshow, though, is I want to clarify some terminology, and I want to give you some phrases that will make your life a lot easier. So I can see the big picture past what we're going to do today. Okay, we have 4 more lessons, not even lessons, 4 more topics, and then we're done for the year. And since I know where we're going, there's some things I'm going to start today that are going to seem kind of overkill, but will be very, very helpful in the future. It'll make sense when we get there. Okay, so area between 2 curves, we got it. We did that between curve, yeah, with top, bottom, with accumulation, and you should be able to properly engage in a conversation. Okay. Introduce yourself, shake hands, eye contact, that kind of stuff. It is sadly lacking in our culture today. Okay, so looking for an area, there's some terminology that we're going to use here. One of them is bounded. What does it mean to be bounded? Bounded creates a region that has a finite area. Okay. There are a lot of bounded regions in this picture. This is bounded. This is bounded. This is bounded. This, not bounded. Goes on forever. Okay? There's the first one. We already know that the integral is going to give us the area under the curve, so we can use that to find some integrals here. Okay? So, if I find the integral of f of x, that's going to be the area under the red curve. If I find the area of g of x, it's going to be the area under the green g curve, the blue curve, sorry, the g curve. Holy smokes. You tell them I'm a little excited about the Batman premiere tonight?
Yeah, whoa.
I know, I kind of like to be sitting in the theater right now waiting for 6 o'clock, but that I have to do this. Sorry. Okay. I don't know what happened to my green area. On my computer screen, there was a green area there. It has mistakenly disappeared, which confuses me. But the green area would have been this guy. And again, we've already done that. So let's move on. Ba, 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 ba. There's the fancy schmancy calculus part. Now, there are some important phrases in there. For instance, g of x must be less than or equal to f of x for the entire interval. That's a fancy way of saying you have to subtract the bottom one from the top one. You can write all that down, but it's irrelevant because all you need to remember is top minus bottom. They even made it change colors. It's that important. I'll do it again for you if you'd like. Yep, that just happened. I'm elevating my transition game. It's only taken me 32 years. You will use that phrase so much in Chapter 7 that you can't help but burn it into your brain. I find top minus bottom easier to remember than g of x must be less than f of x. Because what if you're doing p of x and h of x? It screws things up. Top minus bottom, though, pretty easy to remember. And many of you use that phrase already when we were doing the exploration. Now, this is where things get weird. Everybody, I would assume everybody, was able to find the answer to the exploration problem. But as things get more complicated, I have a process in place that will help you as we move through these problems. And it's called a representative rectangle. Okay, so here's the scenario I have painted. It's similar to what we've done already. We've got a function on top f, we've got a function on the bottom g, and we want to find this shaded region. Okay. What we're going to start doing is creating what's called a representative rectangle. You're saying to yourself, self, that's not a rectangle, that's just a segment. And you would be right, but this is calculus. So in calculus, we have the luxury of saying, oh yeah, that's a rectangle, but it's really, really skinny. How skinny? So skinny, thank you, so skinny that we can't even measure it, so we're going to give it a special name, which I'll get to in a second. Our goal for almost every one of these problems, and the difficult part of almost every one of these problems, is finding the area of that rectangle. If you can do that, the rest of this becomes really easy. Because remember, we talked about the integral being an accumulator. It adds up things. So if I can find the area of that one rectangle, I can use an integral to add up all the infinite number of rectangles throughout the whole problem, and boom, we got an answer. Okay. Now, that seems like a lot of overkill. You all solved that first problem without even the concept of a representative rectangle. You used top minus bottom and everything worked out great. But with the stuff we're going to do in the future, this is going to make your life a lot easier. Okay? Because what we're going to do in the future is we're going to take this bizarre shape here and spin it and create a three-dimensional figure and then calculate the volume. Won't that be fun?
No.
You haven't even done it yet.
Yeah.
Oh, you guys. All right, so let me show you what that looks like in a problem. So I've got this little cat's eye looking thing. One thing you want to be able to distinguish is which function is on top of the other one. If that requires graphing, great. If you just know, that's great. The other thing that you won't always get in a problem is the points of intersection. So that bounded word comes up again. Find the region bounded by the two graphs. In this picture, it's fairly obvious. We're looking for this leaf-looking shape. So I'm going to start with a representative rectangle. It doesn't matter where you put it, as long as it's in the region. Okay. Mine looks like, there it is. Mine looks like that. So I say to myself, self, what's the area of that representative rectangle? For those of you that had a good geometry teacher, you probably remember that the area of a rectangle is, Molly? The area of a rectangle is? Base times height. Very good. So how tall is that rectangle? Don't count. Give me an expression. Give me an expression for how tall that rectangle is, because that's only one possible rectangle. There are an infinite number of them. Why do you look at me like that? You're confused. Matthew.
F of x minus g of x.
Bingo. F of x minus g of x. If I drew my representative rectangle somewhere else, let's suppose I put it over here, it would still be f of x minus g of x. F of x minus g of x. F of x, you get the idea there. But I only care about the green one. So the green one has a height of square root of x minus x squared. And this is where we go back to the idea of how wide is that rectangle. That rectangle is so skinny that we can't measure it, so we're going to consider the width of that rectangle being delta x. Okay, really, really tiny, and since this is calculus, instead of delta x, we're going to use dx. And you see where we're going here. That's the area of one rectangle, the green one in particular. And if I want this whole shaded region, I need to integrate or accumulate all the rectangles from 0 to 1. Why 0 to 1? Because that's the possible locations I could have drawn my representative rectangle. Does that concept make sense? Yes? Good. Question?
So when you're doing the height, it's going to be the top, like, minus the top equation minus the bottom. We went back.
Wait, hold on, I spent all the time doing this. I'm going to show it off again. Look at it. It's going to be top minus, sorry. No, here it is, right? Top minus bottom. Look, you look away! Don't look away from the screen. Look right there.
No, I got it. I was just confused because it said f of x minus g of x.
Wait, did you say you got this?
No.
The thing changing
because
colors?
You said f of x minus g of x, but then you wrote g of x minus f of x, so I got confused.
No, I didn't. Did I?
No, look. Go to
You
your,
wrote
go
it
to
the
your,
right way,
go,
but
you
it's
wrote
not
the right
F of
one.
X
She's f of x minus g of x.
minus
So I got confused.
G.
That's f of x.
Oh,
that's
yeah. Okay. I did it right.
Yeah, you did
He
it
said
right.
it wrong.
Yeah, I was
So we'll blame
confused,
him.
but you said it was
Got
right.
it. I apologize. So I should have yelled at Matthew. That's my
It's
fault.
okay. I was just confused.
The other thing that's really important is we're finding an area, so it should be labeled as such. As we progress through chapter 7, you're going to start with areas, then you're going to transition into volumes. Then you're going to see problems where you're finding both an area and a volume. Therefore, you have to designate to the reader, i.e. the grader, i.e. me or the calc test grader, that you know what you're doing and that you're finding an area and not a body. Okay? Yeah, I did that. Let's see if I got the right answer. I did. Woohoo! Yeah. So smart.
You should be teaching.
Questions? How can we make it more interesting?
Make the little thing go.
What's it? We can throw some trig in there. No, I'm not going to. Okay, never mind.
We're still going.
What we are going to talk about is the second question that you did on the exploration. That is, what happens when the top and bottom changes? Okay. Now, on the exploration problem, you had the luxury of just doing the 2 times thing, or you had the luxury of just switching the top and the bottom. So instead of p of x minus h of x, it became h of x minus p of x. That's pretty much what it is, except when I show you my example, things get a little crazy. So here is the one I'm going to talk about. Things ramp up a little bit. I've got 3 functions instead of 2, but I still have a bounded region. That bounded region, however, is split into 2 parts. Why did I split it into 2 parts? Because if you'll notice across the bottom, when I go from -4 to 2, the bottom changes. From -4 to 0, it's the blue function. From 0 to 2, it's the green function. So what I need to do is simply write 2 different integrals. All right, we don't want to make it more complicated than it has to be. Just treat them as separate regions. Okay, so the first one would be that. That's the red minus the blue from -4 to 0. Remember, the bigger numbers, or sorry, the smaller number is always on the bottom. And then R2 is that red minus green or green minus red? Red minus green, top minus bottom again, gives us that. And again, I don't want to spend time doing antiderivatives. You could FN int that if you'd like. In fact, I would highly recommend that you FN int a lot of these, because that's not really what we're working on here. I'm assuming that you can do those by now. Okay. Good. One more oddity to show you and we're done. And that is, what if my representative rectangle is horizontal and not vertical? Okay, so before we go there, let's review. In these problems, all of my functions are expressed in terms of x. X plus 6, x cubed, -1/2 x. My limits of integration have to do with x values. I'm going from the x value of -4 to the x value of 0. My rectangles, however, are vertical. We're good to go, yes? Excellent. What if we're doing horizontal rectangles? So here are 2 functions that look like, well, sorry, I used the wrong words. Those are not functions. Why aren't they functions? Vertical lines. Okay, very good. I got 2 curves, and I want to find the area between those 2 curves. Now, the first thing you should notice is that the top equals the bottom, so I can just do part of it, but I'm going to do the whole thing. If I did this the way that we did the other problems with a vertical rectangle, it would require 3 different integrals. I need one integral to go from -4 to 0. That'll take care of that. I need an integral to go from 0 to 4 with the top part over there. And then I need another integral to get the bottom part. That's a pain in the butt. If I draw a horizontal representative rectangle, then I can do it in one integral. And it just means changing the way we approach it. If the rectangle is horizontal, then everything is in terms of y. Your limits of integration are in terms of y. So the first thing I would need to do is solve this. I don't know why I phrased it that way, but I would solve this function in terms of x. I keep saying function, I'm sorry. This equation. Okay, so notice, in terms of y, in terms of x. And my rectangle would look like that. Now this creates some problems. Because I don't care how tall that rectangle is. In fact, we know how tall that rectangle is. That's the easy part. That rectangle is dy tall. Really, really small amount of y. How wide is that rectangle? Feel free to describe the answer to that question in terms of the graphs.
2y squared minus 4y minus y squared.
Say it again.
2y squared minus 4 minus y squared.
Close. The other way around.
Y squared. Oh, you do.
Wait,
Red minus blue or blue minus red?
wait, red minus blue?
Red minus blue? Agree or disagree? What? No? You're changing your mind.
I don't
Well, I
know.
Well, you got
said
50-50
minus red.
chance.
I said it was wrong.
I
so
think
you're
it's
right.
red minus blue because you said it's wrong. but it's
Well,
blue
let's
minus
take
red.
a simple approach to it.
Well, it makes sense because it's growth again.
I'm doing this not to insult you, but I'm doing this to help you. If I want to know the distance from there to there, in other words, from 1 to -3, we all know that distance is 4. Do I do 1 minus -3 or -3 minus 1? 1 minus -3, which leads us to our next little buzzword. Where is it? Right minus left. Woo! Oh, sorry, this one doesn't change colors.
Oh, I'm not even remember.
I know I failed you.
I think I had to go.
I know. When early May rolls around, you're thinking to yourself, boy, I really wish I could do this problem, except it didn't change colors, therefore I guess I'm going to get a 1.
I mean, you're right.
This is the start of the decline. I've seen it happen 1,000 times. Everything's going along dreamily until that one problem that didn't change colors, and everything goes to hell in a handbasket.
Wait, so less minus right?
I gotta remember. It's colors.
Don't confuse the matter. It just doesn't change color. I wrote it correctly. It's still right minus left. It just doesn't change color. On a graph, if the problem gives you a graph, don't assume that the point of intersection is something pretty like you want it to be. Don't assume that the intersection is at 4 2's. Could be off a little bit. So how do you find the point of intersection? As I just showed you, you set the function equal. Sorry, I keep saying function. You set the equations equal and solve. So yeah, it is 4 2 and 4 -2, but I wouldn't trust that. So then you set up your equation. So there's the area of the rectangle. This is right minus left. The width of the rectangle. Width. This is the height. So that's the area of the rectangle. Then we use the integral as the accumulator to add all those infinite number of yellow rectangles up. Whoosh. And we get that. Now, you're saying to yourself, self, how do I put that into fn int? Same way you would do anything else. You just change the y's to x's. The answer will be the same. You don't have to change it to y in fn int. Just leave them as x's and it'll give you the same numerical answer. Nobody's going to know that you changed it. Nobody's going to know. Do these concepts make sense? Excellent. I thought they would. Right minus left, top minus bottom.
That's about right.
I'm sorry?
Sounds about right.
Yeah. I mean, top minus bottom, changing colors. Right minus left, does not change colors. Okay, good. Changes colors. We're saved to change colors. Woo! Thank goodness. All right, solve that problem, please. Shut up, Adrian.
I thought we were done.
I forgot we're recording it. Hey, Mom, let's go Mr. Reed. Did you deserve it?
Yeah, pretty well. It's find a bunch of two functions.
As a quick hint, you might want to graph that or sketch it to figure out which one is on top. Do not assume that f of x is on top or that g of x is. Don't assume anything. Because you know what happens when you assume things.
F is on top, so just plug in C.
Telling you broke it. Oh no. Eric fixed.
That what?
So many questions come to mind.
That same color.
I notice he gets
Wait, I'm gonna just straight line to on the next button calculator to bracket.
Graph refuses to load.
I forgot who
It's taking a day off. What's not? I gotta fix your.
Wait, what?
Is it fixed right over here?
Why do you get the picture off the screen, home screen?
Oh.
Did I do that like the week ago?
Do that, yeah.
There's 7 minutes of draw menu?
Yeah.
Okay.
What?
Nice starfish.
I don't know how you can.
Yeah, whatever. So, a week ago, I put a water bottle in one. Maybe plug in a value and I don't have the Y value.
Oh, yeah.
There it is.
I'm sorry, I said, Y value.
That was pretty cool though.
I plugged -7 and then we had to
Did you find the x values?
Oh, yeah.
Either function, the points of intersection, you plug it in either one, plug it in.
What is it?
He wants to go with one good for the first. I have the 2 points of that.
I know you're working, but what are the points of intersection?
3, 0.
3, 0, and?
7, 8.
How'd you find those? Answer the question, please. I mean, the math fairies didn't beam it into your brain. Where did those numbers come from? Calculator, fine. Now, when you're doing the calculator, did you look at the graph and assume it passes through 3, 0, or did you actually do an intersection calculation?
I just looked at the graph.
Okay, don't do that. Use the intersection function. However, the other thing you could do is that. Solve the quadratic. Now, to solve that quadratic, you're going to have to multiply it out a little bit and simplify things a little bit. X squared minus 8x plus 16 minus 1 equals 2x minus 6, and you know how to proceed from there. You should have a quadratic formula on your calculator. You plug and chug, you'll get 3 and 7 as your answers. Plug them back into one of the functions to get 0 and 8. Okay, good. 1/3 of the problem done. Carry on.
X minus 4 squared minus b. Well, you need to subtract.
And you need a dx. Good.
2 minus x is the fifth.
Oh,
Yeah.
Which one?
I'm not arguing.
I love that so
Oh, yeah, it's, it's only in some kind of area.
yeah.
Let's involve it.
Why? I'm just saying
Our rocket's gonna take off at about T minus a couple minutes. We're ready to wait a little bit longer. I know you're all comfortable in that big old capsule. We'll wait a couple more minutes here until, everybody ready now?
There's no more in the bag right now. Someone bought all the other
Good. All right, halt. Stop chatting. Let's debrief then. Which function's on top? G of x, right. For those of you that didn't graph it, but I think you all did, we have a parabola with a line passing through it. So our bounded region goes from that point to that point. This point is 3, 0. This point is 7, 8. So I'm going to go through the representative rectangle process, even though nobody did that, again, because I know where we're going in the future. So my representative rectangle, I'm going to choose to draw right there. How tall is that representative rectangle? Top minus bottom. G of x minus f of x. How wide is that rectangle? Really, really tiny. Dx. So that's the area of one rectangle, and now I want to add up all those rectangles using the integral. From 3 to 7 or 0 to 8? 3 to 7, because again, everything's in terms of x. So we go from 3 to 7. And this is an area, so it should be labeled accordingly. You're writing an equation, not an expression. Walking around the room, I saw people do it two different ways. Everybody I talked to got to this point. How you solved it were two different ways. Some people did it as one big honking thing in fn int, which is great. Some people did 3 to 7 of g of x dx minus the integral from 3 to 7 of f of x dx. Okay. Doesn't matter. You're going to get the same answer. I think it's 10.667, yes?
Yes.
Beautiful. Okay. I will say this. If you get this concept under control, it will make things a lot easier as we move forward. If you get into the problems for 7-1 and you're struggling, you need to get some help. Because otherwise it's just going to get worse as we go on it. But I don't think this concept is that tricky, right?
No.
Right.
Good. Excellent. I found a picture of an old lady dancing. I don't know why it seemed relevant, but it's Friday.
She's vibing.
She is totally. Okay?
She's feeling music. Isn't that one that you get up and down?